So in this section, we're going to be doing L'Hopital's rule. L'Hopital's rule has always been one of my favorite parts of calculus. We want to recognize when we need to apply L'Hopital's rule and also identify indeterminate forms that are produced by quotients, products, subtractions, and powers, and apply L'Hopital's rule in each case. So some of you may have seen this. We generally use L'Hopital's rule when we're trying to take the derivative of something and it gives us something that we call an indeterminate form. So let's just start, and I'm going to identify some indeterminate forms. So let's identify indeterminate forms. And what do we mean by that? Okay, so if I ask you to do 6/2, you can clearly say to me that's 3. I can count 3. I can always get 3 when I do 6 divided by 2. But indeterminate forms are things that are ambiguous in terms of what does it mean. So the first one is 0/0. 0/0 is not 1. It is an indeterminate form. We don't know what it actually equals. It could be anything. Okay, another one is infinity/infinity. It is also an indeterminate form. Another indeterminate form is 0 times infinity. You would think that that would be 0, but it's not. Another one is infinity minus infinity. That necessarily may not be 0. And then we have a couple more. That is 1 raised to the infinity power. Don't know what that is. We don't know what 0 to the infinity power is. And we also don't know what infinity to the 0. So anytime you see one of these numbers or one of these things, you are going to have to work harder to get the solution. You just have to. You cannot leave the answer as that, and you cannot make it to something that you decide to be 1 or anything else. Okay, so when you get an indeterminate form, we have to work harder. Okay, so let's give you the theorem. And the theorem is actually rather easy to utilize. So this is the first theorem, theorem 1. And theorem 1 says, suppose that you have f of a is equal to g of a, and they are both 0. We also want to suppose that f prime of a, g prime of a exists, and g prime of a is not equal to 0. So this is very easy. It says that the limit as x approaches a of f of x over g of x, which would normally give me, if I put in a, I'm going to get 0/0. That just becomes f prime of a over g prime of a. So simply put, if the limit as x approaches a of f of x over g of x is equal to 0/0, then you have to work harder to get that the limit as x approaches a of f prime of x, f of x over g of x going to give you f prime of a over g prime of a. Okay, so how does that work? All right, well, let's look at this problem, something very easy. The limit as x approaches 0 of the sine of x over x. Now I'm going to get the sine of 0 over 0. So that gives me 0 over 0. So now I'm going to use L'Hopital's rule. So my symbol for that is a little crooked arrow with an LH. That lets me know that I'm now going to invoke L'Hopital's rule. So therefore the limit as x approaches 0 of the sine of x over x becomes the limit as x approaches 0. Take the derivative of sine, I get cosine of x. Take the derivative of x, I get 1. So now I get the cosine of 0 divided by 1. That's 1 over 1, which is 1, and I'm done. Okay. So it's not difficult theorem at all. I have the limit as x approaches 0 of e to the x minus 1 divided by the sine of 2x. And when I put in 0, I get e to the 0 minus 1 divided by the sine of 0. E to the 0 is 1 minus 1 divided by 0. So now I get 0 over 0. Okay, that's my indeterminate form. Let's invoke L'Hopital's rule. So now I can just take the limit as x approaches 0. Let's differentiate the top. When I differentiate the top, I get e to the x, because the derivative of e to the x is e to the x. Derivative of 1 is 0. Derivative of sine of 2x is 2 times the cosine of 2x. So now when I put in 0, I get e to the 0 divided by 2 times the cosine of 0. So this is 1 divided by 2 times 1, which is a half. Okay, any questions? Any questions? All right, I'm going to do one more, and then I'm going to give you one. All right, this one is a little strange. This is the limit as x approaches 1. In the numerator, I have 1 minus x plus the natural log of x. And in the denominator, I have 1 plus the cosine of pi times x. So please put 1 in there for me and tell me what you get. Anybody get an answer yet?
So at least I know for the top one, it would be, I think, -1 plus 1 over x for the numerator of number 3.
Okay, so we're putting in the number 1, right?
Yes, -1.
Okay, so I'm going to end up with 1 minus 1 plus the natural log of 1 divided by 1 plus the cosine of pi. So 1 minus 1 is 0, and the natural log of 1 is also 0. So I get 0, and I'm going to get 1 plus -1, which is going to give me 0 over 0. So I am prime ready to use L'Hopital's rule. Okay, Eric, do you see that?
I was wondering though, like, are you the math you doing? Are you
Say that again.
like, I'm, I'm, just, I'm just wondering, are you trying to just do like the basic math, or are you trying to find the rhythm? I'm not sure like how you get like the 1
Okay,
plus the
so
1.
I'm actually, okay, good question. So I'm actually just trying to find limits right now. So we use L'Hopital's rule when we're trying to find limits. And so when I look at the limit and I'm trying to take, as x gets close to 1 of this function, when I do direct substitution, which is the first way you do a limit, when you do direct substitution, you get 0 over 0. So now that I've gotten 0 over 0, that means that that is an indeterminate form. I cannot leave my answer like that. I have to move forward. So 0 over 0 allows me to invoke L'Hopital's rule. So L'Hopital's rule says take the derivative of the numerator and take the derivative of the denominator. Okay, so when I take the derivative of the numerator, I get the limit as x approaches 1. So the 1 goes to 0, the negative x goes to -1, and then log of x is 1 divided by x. In the denominator, the 1, the derivative of that is 0, and the derivative of cosine pi x is negative pi cosine of pi x.
So, Professor, so why did we put the negative pi on the left side?
Okay, because
I know the derivative of cosine is negative sine. But why is the pi? Why did you put the pi on the left side?
okay, because the derivative with respect to x of the cosine of any constant times x, when I get that, I'm going to get minus the sine of that constant times x. But a chain rule says I have to multiply by that constant. So this just
That
turns
makes
out
sense.
minus k. You got it? You got it now?
Yes.
No problem. Okay. All right, so now I'm going to evaluate it. So when I put in 1, I get -1 plus 1, and then I divide, and I get negative pi times 0. So this gives me 0 over 0 again. Uh-oh. Man, I got to invoke L'Hopital's rule a second time. I still haven't gotten where I need to be. So now I'm going to do the limit as x approaches 1. I need to take the derivative of the numerator, and that is -1 over x squared. And then I need to take the derivative of the denominator. So the derivative of sine pi x is going to pop out another pi. So now I'm going to get minus pi squared cosine pi x. So this time when I put in 1, I'm going to get -1 in the numerator. In the denominator, I'm going to get negative pi squared. And the cosine of pi is -1. So my answer is -1 over pi squared. And I'm finally done. It took 2 tries, but I'm there. Okay. Here's one for you to do. The limit as x approaches 0. Yes, 1 minus the cosine of x over x. Okay, so I want you to work on that one. Okay, any answers?
So for
You're breaking up just a little bit, Diara.
I've got -1 over 0, which is an error.
Okay,
hello.
yes.
So wouldn't you have to take the derivative?
Well, you got to prove to me first it's 0 over 0.
Do we
So you
plug in
get
0 for x?
1, yep, 1 minus the cosine of 0 over 0. So first you got to prove to me that you can use the rule.
Oops, that's a lot. Correction. It's actually 0 over 0. I actually
Well,
took the derivative of 1. It's actually 0 over 0.
0 over, so you're not taking any derivative yet. No derivative. This is direct substitution first.
Why aren't you taking a derivative?
Okay. I take the derivative after I show you that it's 0 over 0.
Oh, okay.
I got to do that first. So no, go back to look at every problem. Every problem I proved to you it was 0 over 0 first, didn't I?
Yeah, and then you
Okay.
took the derivative.
And then I took the derivative. Okay.
Okay.
So do direct substitution. Show me you got 0 over 0. Then you can use L'Hopital's rule. Okay, so now I get the limit as x approaches 0. What's the derivative in the numerator? What do I get?
So would it be sine x, because the derivative one is one's a constant, so it's 0. And then the derivative of cosine is negative sine, but we have a negative cosine. So the negatives cancel out, correct?
That's correct. And the derivative of x is 1. So now I just get the sine of 0. And the sine of 0 is 0. And I'm done. Okay, so here's theorem 2. If limit as x approaches a of f of x is infinity, and the limit as x approaches a of g of x is also infinity, then you get the limit as x approaches a of f of x over g of x. This gives you infinity over infinity. Oh, now I got a different one. I got infinity over infinity. I didn't get 0 over 0. But that implies then you get to that equal the limit as x approaches a of f of x over g of x is equal to limit as x approaches a of f prime of x over g prime of x. So the second part of the theorem says this also works if I get infinity over infinity. The limit as x approaches infinity of the natural log of x divided by the square root of x. So the log of infinity is infinity, and the square root of infinity is infinity. And so there I am. I'm looking at infinity over infinity. So by L'Hopital's rule, I can take the derivative of the top and the derivative of the bottom. The limit as x approaches infinity, the numerator is 1 over x. The derivative of the denominator is 1/2 x to the negative 1/2. Simplify that. That becomes the limit as x approaches infinity of 2 over the square root of x, just by simple algebra. So now when I put in infinity, I get 2 over infinity, but we all know that that's 0. The limit as x approaches infinity of e to the x divided by x squared plus x. E to the infinity is infinity. Infinity squared plus infinity is still infinity. So now I have infinity over infinity. Another indeterminate form. So let's use L'Hopital's rule. Okay. So I take the derivative. Derivative of e to the x is e to the x. The derivative of x squared plus x is 2x plus 1. So e to the x goes to e to the infinity, that's infinity. And 2 times infinity plus 1 is still infinity. Got to do it again. So I get the limit. X approaches infinity. E to the x. And then the denominator just becomes 2. Okay. So e to the x goes to infinity. Infinity divided by 2, well, geez, that's still infinity. So now I have an answer. Okay, one more. This one is not, the limit's not going to infinity this time. I have the limit as x approaches pi over 2 from the left. Okay, so this is a one-sided limit of the secant of x divided by 1 plus the tangent of x. Okay. The secant of pi over 2 is 1 over the cosine of pi over 2. And the cosine of pi over 2 is 0. So that's just infinity. And the tangent of pi over 2 is also infinity. Okay. All righty. So I'm going to invoke L'Hopital's rule. So I'm going to take the derivative. What's the derivative of the secant?
1 over cosine x.
No, that is the definition of the secant. I want the derivative of the secant.
Is it a negative cosecant?
Actually, it is not. Okay, we need to do some review. I never have a problem doing a review. I will do a review because I want you guys to know it. Okay, so the derivative of sine is cosine x. Derivative of cosine x is negative sine x. Derivative of tangent x is secant squared x. Derivative of cotangent of x is negative cosecant squared x. Derivative of secant x is secant x times tangent x. And derivative of cosecant of x is negative cosecant of x times tangent x. Okay, so they are our derivatives. Okay. So we needed a little refresher. There's nothing wrong with that. Okay, we're in Calc 2, so sometimes we forget of stuff way back from Calc 1 that we haven't used in a while. So now I know the derivative of the secant is secant x tangent x. And please know, I certainly appreciate those who attempt to give the answer. And the derivative of tangent is secant squared. Okay, so this now becomes the limit as x approaches pi over 2 from the left. I can cancel one secant, so this secant can cancel with that one. And that gives me the tangent of x over the secant of x. Okay, well, let's do some work here. This is the limit as x approaches pi over 2 from the left. The tangent of x is the sine of x over the cosine of x. And I'm dividing by the secant, which means I multiply by the reciprocal. So this just gives me the limit as x approaches pi over 2 from the left. The cosines are going to divide out, and that is going to give me the sine of x, and the sine of pi over 2 is 1. Okay. Any questions about that?
Hi, Dr. Locke. I have a question about the derivative of tangent x.
Yes.
So you got sine x as the derivative of tan x, but on the table here,
Oh, no,
it says tangent x is,
And the derivative of, no. So let's go back. Right here, I had secant x, and I took its derivative, secant x tangent x. I took tangent x, and I took its derivative, secant squared. Then all the rest of the other stuff was simplifying the problem before I took the limit again.
oh, so you already took the derivatives then. Okay.
So, yep. So I had already taken the derivative in the second line. I took the derivatives. But now I needed to simplify what I got. So tangent x over secant x and then to sine x are all simplifications before I evaluate the limit.
Gotcha.
Okay. Any other questions? Okay, so far we've looked at using L'Hopital's rule for 0 over 0. And we've looked at using L'Hopital's rule for infinity over infinity. Now, those are the only 2 times you can use it. You can't use L'Hopital's rule for anything else. So what happens when you get a different indeterminate form? All right, so let's look at other indeterminate forms. So the 2 I want to focus on now are 0 times infinity and infinity minus infinity. So I want to focus on these 2. Okay, so if you get 0 times infinity or infinity minus infinity, okay, you have to rewrite it. You must rewrite it. Rewrite the limit to get 0 over 0 or infinity over infinity to use L'Hopital's rule. So you cannot use L'Hopital's rule on 0 times infinity or infinity minus infinity. But if I do a little tweaking and make it look like 0 over 0 or infinity times infinity, I'm sorry, infinity over infinity, then I can do it. So here's an example of that. So in the first problem, I have the limit as x approaches 0 from the right of x times the cotangent of x. Okay. The cotangent of x is the cosine of x over the sine of x. So when I take the limit as x approaches 0, x is going to go to 0, but the cotangent is going to go to infinity. So now I have 0 times infinity. And 0 times infinity doesn't help me at all because I'm stuck. If I could figure out a way to rewrite that, I would be in good shape. So let's try to figure out a way to write infinity as 1 over 0. So let's write this as the limit as x approaches 0 from the right. So I'm going to write this as x times, and this now, the cotangent is 1 over the tangent. So now this is the limit as x approaches 0 from the right of x over the tangent of x. So all I did was rewrite my expression. So I wrote cotangent as 1 over tangent. And by writing cotangent as 1 over tangent, now when I take the limit as x goes to 0, x goes to 0, and the tangent of 0 is 0. So yay, I have L'Hopital's rule. I can use L'Hopital's rule. Oh, let's use blue. So now I didn't change the problem. I just rewrote it using trig identities. So now I can invoke L'Hopital's rule because now I have 0 over 0. So this is the limit as x approaches 0 from the right. The derivative of x is 1. We said the derivative of tangent is secant squared. So as x goes to 0, I get 1 over 1. So this answer is 1. So note, infinity times and 0 times infinity, I don't know what it actually could equal, but it doesn't equal 0. For this problem, it gave me an answer of 1. Any questions about that? So notice how I flipped it so that it would work for me. Okay, here's another one. The limit as x approaches 0 of 1 over x minus 1 over the sine of x. Now 1 over 0 is infinity. And then sine x is also 0. So now I have infinity minus infinity. So that's a problem because it being infinity minus infinity, it still doesn't look like either one of the L'Hopital rules that I could use. I don't have 0 over 0 or infinity times infinity. So I'm going to simplify this. So I'm going to simplify 1 over x minus 1 over sine x by putting it over the same denominator. So notice I can't invoke L'Hopital's rule yet, but this is going to be the sine of x minus x divided by x times the sine of x. That's the same problem. So these two things are the same. This is the same as that. Okay. So now when I take the limit, I get 0 minus 0 divided by 0 times 0. So now I get 0 over 0. And yes, I am very happy because now I can invoke L'Hopital's rule. Had to do a little work, but I'm there. Okay, so now I'm doing it. Now that I know that I have 0 over 0, now I'm going to go ahead and take the derivative. Now, it doesn't look quite fun because the derivative of the denominator is a product rule, but it's doable. So in the numerator, derivative of sine is cosine x, and derivative of x is 1. And in the denominator, I have to use a product rule. So I get the derivative of the first times the second, plus the first times the derivative of the second. Okay, so now when I go to put in 0, I get the cosine of 0 minus 1 divided by 0 plus 0 times the cosine of 0. So this is 1 minus 1 divided by 0. So I get 0 over 0 again. Well, my goodness, I got to go back and do L'Hopital's rule a second time. So here's the thing, guys. You cannot give up in the middle of a problem. At this point, somebody would say, you know what, this problem is too long, or it's too frustrating, or it's taking too much time. You're almost there. Just keep going. So now we got to take the derivative of the numerator and the derivative of the denominator again. So we're going to invoke L'Hopital's rule a second time. So this is the limit as x approaches 0. In the numerator, derivative of cosine is negative sine of x. In the denominator, the derivative of the sine of x is cosine x. Plus, I have to use a product rule. So I'm going to do derivative of the first times the second, plus the first times the derivative of the second, and this time I get 0 over 2, but that's just 0. So now I have an answer. Okay, so we've shown what to do for L'Hopital's rule. So when we get 0 over 0, we're going to differentiate the numerator, differentiate the denominator, and reevaluate the limit. We get infinity over infinity. We're going to differentiate the numerator, differentiate the denominator, reevaluate the limits. We get 0 times infinity, we need to rewrite it so that it looks like 0 times infinity. I mean, it looks like 0 over 0 or infinity times infinity. And if I get infinity minus infinity, I'm also going to rewrite it. So the last case is when you have indeterminate powers. And those are the last 3 indeterminate forms that I talked about at the beginning of the lecture. Okay, so this last case is we take the limit. So suppose the limit as x approaches a of f of x turns out to be 1 to the infinity, 0 to the infinity, or infinity to the 0. So I do the limit of the whole thing, and I get something that looks like that. So what we're going to do is we're going to take a logarithm first. So you're going to take that, and then you're going to find L, which is going to be the limit as x approaches a of the log of f of x. So you're going to find that limit, and then you're going to conclude that the limit as x approaches a of f of x is e to the L. So it's a three-step process. And so here's an example. So we need to compute the limit as x approaches 0 from the right of 1 plus x to the 1 over x. Now that looks really like a hot mess. Okay. So we're taking that limit. We want to try to find that. So the rule says first take the log of that. Okay, so let's take the log. So we're going to get the natural log of f of x. Turns out to be the natural log of 1 plus x to the 1 over x. Now there had to be a reason why I wanted to take the natural log, and the reason is because the log of something to a power, I can bring that down. So that's now simply 1 over x, the natural log of 1 plus x. Okay, I did forget a step. If I put in x equals 0, I get 1 to the infinity, and that's unsatisfactory. Okay, so when we do the direct substitution, we get 1 to the infinity. So we're not happy with that. So we're going to take the log. So now that I have taken the log, I'm happy with this logarithm. It's nice. Now I need to compute. So that was step 1. So step 2 tells me to compute the limit as x approaches 0 from the right of the new function, which is 1 over x times the natural, well, let me write the whole thing. The natural log of f of x, but that's the limit as x approaches 0 from the right. We made it 1 over x times the natural log of 1 plus x. And if I plug in 0, I end up with the log of 1, which is 0, over x, which is 0. And yay, I now have zero over 0. I didn't start off with 0 over 0. I started off with 1 to the infinity. 1 to the infinity did not make me happy. Okay, so therefore now I'm going to invoke L'Hopital's rule because I can. And I get that the limit, oh, this is step 3. The limit as x approaches 0 of the natural log of 1 plus x divided by x.
Professor,
Yes.
1 over x, is this is that an exponent to the natural log of 1 plus x?
Yes.
All
So let's look at our rule. Oh, I got 3 people in the chat. Y'all gotta start talking, Because I don't know. Okay.
I only said professor because I didn't think you heard me.
Oh, I'm glad. I didn't. No, I want you to. I want you to say professor when I can't, because when you're, I don't always see the chat right away. Because I'm writing on a huge tablet. So I don't always see the chat right away. Okay, so yes, Diara, the natural log of 1 plus x to the 1 over x. Remember, you can bring that power down. The natural log of 1 plus x. You can bring that power right on down. It just comes right on down to the front, just like that. Okay. So now let's take the derivative of the numerator. What is the derivative of the numerator?
1.
I want the derivative with respect to x of the natural log of 1 plus x. I think she's got some connection issues. What's the derivative of that? That's the derivative. You guys have not been practicing. You've not been practicing. That is the derivative of the log of some function. The function goes in the basement. And its derivative goes on top. That's it. Okay, any questions about that? Okay, so in here,
I want to say something to, is it okay if I say something to the students?
yes,
Can we make a group chat, please? Can y'all send y'all number and the thing so we can make a group chat if y'all listening? That's what I wanted to say. Thank you.
you're welcome. There's also, I can create a discussion board on Blackboard as well. Who is Q? Okay. Whoa, that's not what I was trying to do. Okay. Any questions? Ayana, you wanted a group chat. Is that because you want to go over some problems with your classmates?
Yeah. And I'll
Okay.
be calling like my
What'd you say? I can't hear her.
Can you hear me?
No, what did you say?
I said yeah, and I call the same two people like if I get confused on a homework assignment or something. Like when I got confused on homework last week, I call the same two people and they'll be just as confused as me. And I'll be like, dang, so what we about to do? And they'll be like, well, we could ask about it in class, but by the time we get to class, the homework done due. So I'd rather have other insight than just my two friends.
Okay, and you also have office hours. I'm available.
Are they on Friday?
I have office hours on Friday. I have office hours every day except for Thursday. Thursday, they're by appointment, which means if you do need to see me on Thursday, you need to send me an email. But I have office hours every day of the week except for Thursday.
Okay. Well, I will be in office hours tomorrow, definitely.
Okay,
After I look at the homework tonight, because I always do the homework on Thursday nights.
okay. All
Okay.
right,
Thank you.
so no problem. Okay, so we're taking the derivative here. So we know that the derivative of the numerator is 1 over 1 plus x. And the derivative of the denominator is just 1. Oop, I forgot my limit. So I get the limit as x approaches 0 of, this is not step 3 yet. I didn't get there yet. Of, this becomes 1 over 1 plus x. And then the derivative of the denominator is just 1. So this just becomes 1. So what does step 3 say? Step 3 says, take whatever you get and make that the solution is e to that number. So the number we got is 1. So in step 3, we now can conclude that the limit as x approaches 0 from the right of 1 plus x to the 1 over x is e to whatever we found. So we found 1, so that's e to the 1, which is just e, and we're done. Okay. Any other questions, comments?
Excuse me, Dr. Locke.
Yes.
For step 2, when you're doing the limit from x to infinity, I was wondering if going off that Hopital's, I'm sorry, I was wondering why the limit that was under the LIM went from x to infinity to 0. Is that when you just, if you start doing
The problem, no, for this whole problem, the limit was 0.
whole problem was 0?
Yeah, so for this problem, the limit as x went to 0.
Okay.
Yeah, I didn't change it in the middle. The other problem, I may have had the limit as x went to infinity. I think that was 1 back here. Yeah, so 1 back there, but this one was, it went to pi over 2. Here it went to 0. Here it went to 0. And this last one, it went to 0. Okay.
Okay. Well, thank you.
Yeah.
Professor, I have a question as well.
Yes.
When we conclude on step 3, right at the last step, we raise e to whatever it is that we got, like
Whatever you got. That's exactly right. You raise the e to whatever you got. So if you got 1/2, it would be e to the 1/2. If you got -1, you'll be e to the -1. Whatever you get. So you compute L in step 2 is your limit. You compute that limit in step 2, and whatever you get, you call it L. Whatever you get, you call it L. And then in the end, you take e to that L. So we went through the limit. We took the log. We simplified it, got 0 over 0, used L'Hopital's rule, got the L to be 1. And so therefore the solution is e to that 1, which is just e.
Okay, thank you.
You're welcome. Any questions?